Hey everyone, welcome back to another episode of Flying with Spurts. I know it's been a while since my last upload. I had talked previously about how I was going to have a delay in my warbird testing. Fortunately, I think that delay is coming to a close. Unfortunately, a few other things have popped up in the meantime, such as the new F-16 flight model and the release of the Apache, which I had pre-ordered. So before I resume my warbird testing, Rogue and I are probably going to do a few Apache videos. I should be able to resume the warbird testing soon. Now, about the Viper FM. If you watched my first long vid, part 1, about me, you may recall that the F-16 is kind of what really got me into military aviation. So the release of a new flight model for the Viper is very exciting for me. Now I know this new flight model was released about a month ago, so I'm a bit behind the game on having a new video about it. However, while most other videos have been about how much more powerful the Viper is in a turning fight, if you know me from F16.net, you know that I only care about accuracy. So I'm going to be looking at whether the new flight model is more accurate than the old flight model. So just before the flight model was released, I set up a mission with a specific loadout to simulate a drag index of 50 and a weight of 26,000 pounds. For this one mission, I turned off GFX and I turned on unlimited fuel. What this allowed me to do is to take page 462 of a certain European user's F-16 manual that has a energy maneuverability plot. So while this is not actually the chart for the United States Air Force F-16 that we have in the game, mechanically it is the same plane, or close enough that when I'm correcting to the weight, everything else is going to fall in line. So I used the 10,000 foot flight regime and drag index of 50. Now why did I do that? I did that because I wanted to be able to test a condition where the F-16 never gets stuck at 9 Gs due to its high thrust. I wanted to be able to be at any speed, pull the stick into my lap, and have it slow down. So while in some places this document is easily accessible online, for security reasons I'm not going to show any pages of the document. I will, however, show some data that I pulled out of it. For my testing methodology, I recorded an energy bleeding turn, and then loaded up TacView, set this play speed in TacView to 1/4 speed, and then use the arrow keys to advance time, and then as soon as a new second ticked off, I would release the key. There's a little bit of noise in how quickly after each second I can release the key, and there's a little bit of noise in the way TacView records data. So while there may be noise in the data plots, the general trends will be correct. So some of the things that were fixed with this new flight model update was the G available, impacting the instantaneous turn rate, and a change to the pitch rate. Now, pitch rate is not to be confused with turn rate. This is about how quickly the airplane can increase or decrease its angle of attack. The top set of plots is instantaneous turn rate, as the title suggests, and the bottom two lines are actually sustained turn rate. I just put them on the same plot for convenience. So if we look at the instantaneous turn rate plot in isolation, we see that the thick dark gray line is the flight manual's line for what the maximum turn should look like. And we can see the light blue line for the old flight model, how it was fairly well below that early on. This is because the original flight model had quite a bit of difficulty reaching 9 Gs. But once you slow down below 8 Gs, it's more or less on track. The new flight model greatly improved the ability to reach 9 Gs or thereabouts. So that's why the red line for the new flight model is very, very close on the right end of the top curve. But I noticed that it tends to completely overshoot the top and back side of the curves. Now, why is that? My initial reaction was that it looks like it's actually allowing for too much angle of attack to take place. Now, looking at why instantaneous turn rate seems to go so high, what it looked to me is that the Cat 1 limit was not being followed. Now, the Cat 1 limit is something fairly unique to the F-16 in that it changes the maximum allowable angle of attack with the maximum allowable G. I did not do a test of sustained turn data with the old flight model, so I'm not actually sure whether or not any improvements were made here. But really what I noticed is that from 0.7 Mach down to a little bit above 0.3, it follows pretty closely. But at 0.8 and 0.9 Mach, it's a little slow. Now there's apparently an acknowledged bug where wave drag of munitions is too high at the moment. So that would explain why we're seeing that. PSABS, or specific excess energy, is a measure of how quickly an aircraft can accelerate or decelerate in a level turn, or whether they should be climbing or descending. Now fortunately, I know the equations enough to be able to take a change in speed over time and equate that into a PSABS. And then when I was doing my tests, I did also record the altitude, as you can kind of see in the data off to the left. So I was able to measure the total change in the energy state and thus give myself a PSABS. Also of note, for the turn testing, I was measuring the track intact view instead of the heading, because the heading will change with angle of attack, while the track is about the actual flight path of the aircraft and thus the true turn rate. The top part of the graph is a level flight acceleration. The bottom part of the graph is the deceleration at maximum pull. What I found is that the old flight model, again, is pretty close at the slower speeds, and the new flight model actually bleeds more speed at the lower speeds. But as we saw, it's also having a higher turn rate. So we see that with the old FM, at higher speeds, the deceleration is not high enough. But that would also be expected if you're not turning fast enough. You're not pulling enough Gs. And if you're not pulling enough Gs, then you shouldn't be bleeding as much speed. Also of interesting note is that, for the most part, both of the accelerations of the old and new flight model are very close, within noise, but they are also far too low compared to what the flight manual says they should be. So, looking at this, let's talk about why the new flight manual feels the way it does. Why does it feel like it's so much easier to pull someone into your HUD? As we saw before, the instantaneous turn rate has been improved across the board. So when you're at a maximum pull turn, you will be turning faster, but you will also be bleeding speed quickly. And the improvements to the pitch rate means that you can get from a sustained turn to a maximum turn very quickly. Now, what about the fact that it feels like it recovers energy so much faster? When I'm looking at these acceleration charts for old and new flight manual, and it seems like, if anything, the new flight manual recovers energy slower. Again, the difference here is nitpicking. This is noise. The reason why the new flight manual feels like it recovers energy so much faster is because you're no longer stuck at a high angle of attack. It used to be that if I got slow, I had to push the stick all the way forward and wait a few seconds for the nose to really come down so that I could start building up speed again. Now, the nose comes down as soon as you let off back pressure, and if you push the nose down, your nose is down almost instantly. So from the time you decide to start recovering energy until the time you have recovered energy is several seconds faster because of the improved ability to lower the nose. Now, to test my theory about having too much angle of attack and thus making too much lift, too high of a turn rate, and too much bleed accordingly, I theorized that what was happening is that the Cat 1 limit is not being followed. So I went in and did another test, specifically looking at how the angle of attack and G relate to each other as speed decreases in a maximum pull turn. And as you can see, over most of the range, the new flight model allows more G for a given angle of attack than it should, or more accordingly, it allows a given G to be achieved at a higher angle of attack. So it's not pulling the turn rate down the way that it should, especially once you make it past that bend at about 7¼ Gs. And where is 7¼ Gs on a turn rate plot? It's right about the back end of the plateau. So if we look, the data is pretty close at 9 Gs. I would even say within noise. By the time we get to 8 Gs, we see that we have about half a degree angle of attack more available. That may not sound like much, but at the high speeds we're talking about, even a small improvement in angle of attack gives you enough lift to drastically change your available turn rate. See that once we get to 7 Gs, we're looking at almost an entire degree of angle of attack. And at 6 Gs and 5 Gs, we're actually beyond a full extra degree of angle of attack. So in effect, the new flight model actually is turning too quickly and bleeding speed too quickly as a result. I think that the speed bleed it's currently exhibiting is proportionate and correct for the amount of turn that it's producing. But between the issue with not following the Cat 1 limit more correctly, which if it did would probably fix all the instantaneous turn rate issues, and the fact that we seem to be underperforming in level acceleration, as fast as it already is. It seems like there's still a few tweaks before we get a Viper flight model that's really on the right track. Overall, this is still an improvement. Just understand that it's not perfect yet. And if ED does decide to fix this, remember, this isn't them nerfing it for balance reasons. If they get it to follow the Cat 1 limit more properly, this is a correction for incorrect implementation. So that summarizes my analysis on the new F-16 flight model. Thank you for your time and your patience. Hopefully, I will begin to resume flight testing warbirds and put up some Apache videos for you soon. See you next time.